Hi, everyone. Thank you so much for coming to my talk. I am super excited to be here and talk to you about distributed data stores on Kubernetes and some Kubernetes concepts that help make it easier, and about some other pretty new, interesting distributed things on Kubernetes. I am Alena Hall. I live in Seattle. I am a senior cloud developer advocate at Microsoft working on Azure, focusing on big data and distributed systems. I also really enjoy trying out new things and experimenting with stuff, so like in this talk. And as a starting point, I will assume that you are able to create a Kubernetes cluster. There are many ways to do so with different cloud providers or machine sizes and other settings. I have used Azure Container Service, Azure Kubernetes Service, created with Terraform for my setup in this talk, but if you are using something else, it should not matter at all. It will be equivalent. And we're also going to be using Cassandra in this talk as an example. For those who have not worked with Cassandra, I will do a brief overview, but I have a more in-depth blog post about it, and I'll share it later at the end of the talk. One more thing you will probably need is also courage or a sense of adventure, because combining technology like Kubernetes and something like Cassandra, a system that requires stable persistence, that might not sound like everybody would be immediately willing to do this without thinking about consequences. So when we talk about data and databases, they are arguably one of the most important parts of any system. And we wouldn't want to deal with any data loss or spend hours recovering from a mistake that can cost significant amounts of money. So I generally wouldn't use a technology in production unless I'm 100% confident in it. Well, it's probably not possible to be 100% confident in anything, but general message is that if you don't feel sure enough, and if the system, like database system that you're using works well on physical machines or virtual machines or anything else, then that might be a good way to go. But this talk is not about this. We're going to talk about containers and Kubernetes and how it can make it faster and faster basically to get it up and running. But it won't really simplify day-to-day management and operations on your database cluster. So now let's talk about why and when it might be a good idea. Flexibility and possibilities that Kubernetes provides, they actually have proven to lead to more frequent Kubernetes service deployments. It also reduces some operational efforts that have to be put in recovering individual services. And it automates a lot of common operations to support healthy lifetime of services, and is generally pretty convenient to manage multiple services altogether. So what is the benefit of running a distributed database on Kubernetes? Well, it might take a long time to properly set up your database system using physical machines or virtual machines. And once you get it up and running, you will most likely leave it up and running and wouldn't want to mess with it. If we're thinking about containerizing our database deployment, it is very fast and easy to get it up and running, so we won't have to keep it there when it's unused. It takes just a few minutes to deploy it and to destroy it, so it's perfect for dev and test clusters. But there are companies who use Kubernetes for databases in production today also. So here is a talk plan. Quite a few things to cover. But first of all, I know that some of you might have some knowledge of Cassandra and Kubernetes, especially after Eric's talk. But if some of you don't have it, I will do a brief and quick refresher. So there we go, Cassandra. Cassandra is a very powerful distributed database. It's very highly available. It scales really well. It is an AP system in terms of cap theorem. And to be more specific, it uses a ring topology cluster. So when the new data arrives, the cluster already knows what node to put the entry on. because each node in the cluster is responsible for specific limited hash range from the overall hash circle ring. Also, based on the partition key of the data, we know what node is responsible for this data, but most likely the data entry will be stored on more than one node if the replication factor is more than 1. It is also a highly available system which is masterless, and all nodes can act as a coordinator. For example, if there is some request for data entry that is stored on node A that came in through node B, and if node A went down unexpectedly, then node B would store the request with changes necessary in its hints table, and as soon as node A comes back up, the node B will notify node A about the request. So even though Cassandra is an AP system, it doesn't mean that we always have to sacrifice consistency. We can also tune consistency on the per query level. So the general rule we can have for consistent queries is write quorum plus read quorum should be more than a replication factor. And the important thing is that we can get really fast reads if we query by partition key, because all the data is stored on the same, together on the same level physically. So yeah. Writes are pretty fast because they are written into immutable append-only commit log, and also to the per column family structure called mem table, which is residing in memory. And when it gets full, it flashes to disk into a format called SS table. And where too many SS tables, they get compacted into a bigger SS table. So that's a pretty good intuition about what Cassandra is. Now, Kubernetes is a distributed system for running more containerized distributed systems, I would say. Some of the features that it provides are scheduling and resource management, scaling, rollbacks, self-healing, secrets, service discovery, jobs execution, and more. It also has a concept of nodes and pods. Node itself is not created by Kubernetes. It's created externally, like we can use Azure or Google Cloud to provision nodes, but it is an object in Kubernetes, and Kubernetes does some checks to make sure that a node is valid. And each node has services necessary to run pods, and there are some management components. So services on nodes include kubelet that checks that containers are running and healthy. There's container runtime like Docker, and kubeproxy for connection forwarding. So nodes can have one or more pods running, and pod is a group of one or more containers, which is basically the simplest unit you can deploy on Kubernetes. It can have an IP address or volumes attached. It's just a simple way to run your container. So nodes can also be master nodes. And so when we submit our resource definitions, which is like a YAML file or a JSON file or through Helm charts, basically we have an API server that waits for read and write requests, and a control loop that checks looks at the current state of the cluster and the desired state, and brings current state to the desired state. And there is a scheduler that watches pods that don't have node assigned and assigns them to the node. And as Eric mentioned, there is etcd, which is a highly available key value store for cluster data. Now, pods by themselves are pretty weak. However, they're perfectly good for building out other abstractions on Kubernetes. For example, deployments or replica sets, which is an abstraction on pods that will always keep a certain number of pods running at all times. If something goes wrong with one pod, it will create another one, which is great for services. That's cool, but aren't containers meant to be ephemeral and used for stateless services? Standard containers kind of are meant to be stateless and ephemeral. They will lose and forget your data in case of restart or an error, so it's not a good idea to save anything that needs persistence on them. Now, how does that do us any good if we want to run distributed databases then? Because those are definitely a system that needs stable persistence. Let's look at what else we got here. I mentioned that pods can have volumes attached. So a volume can store data, but the lifetime of the volume is limited by the lifetime of a pod who owns it. Volume actually outlives the containers within a pod. So if a container restarts, the data will not be lost. Kubernetes supports many types of volumes, and you can attach many of them to a pod. So what if we try deployments or replicated containers with volumes? If we look at it a bit further, we notice that having volumes is not really enough for running distributed databases, because there are certain assumptions that need to be made about the database cluster nodes before we actually create the cluster. So some of the nodes should have roles like leader, follower, or we might have some nodes designated as seed nodes, and we need them to be discoverable. So standard containers are not persistent. Even combined with Kubernetes volumes, there are quite a few issues. We notice that pods start up with non-deterministic and random names that are not predictable enough, and that they start in random, unpredictable order. Same with deletion and termination and scaling. So we can't really make those distributed system assumptions. So replica sets with volumes won't work for us. So before creating the database cluster, we need to have certain guarantees about the database nodes. They should have discoverable names. They need to start in predictable order for us, and they need to have persistent storage. So let's look at another Kubernetes concept that helps make it possible. It's called Stateful Sets. Stateful Sets are kind of similar to Kubernetes deployments in a way that they always keep a certain number of replica pods running. But they're different because they have an identity. So each pod will start with a unique and stable network identifier. It will have stable and persistent storage attached, and there will be a persistent link from pod to storage. And all of the pods in the stateful set also start in the same order, get terminated in the reverse order, and it is preserved. So if we look at the possible architecture of using stateful set with, let's say, Cassandra on Kubernetes, it might look something like this, where we have Kubernetes, we have some Cassandra pods, each of them has ordinal index, and each of them have persistent storage attached. Now let's actually unpack the definition of a stateful set. We know what it guarantees, but what is it really? So it starts with a headless service. This is a kind of service that is called headless because it does not need a cluster IP available, and we don't do any load balancing with it. The service definition has a selector, and when the service is accessed, the DNS is configured basically to return a list of A records or addresses which point directly to those pods that have the same selector. And we needed to manage the network identity for those stateful pods. To create a headless service, for Cassandra, for example, we can use a similar template, which defines kind service and defines that cluster IP is none, label Cassandra, and the port 9042. So now let's talk about the actual storage for stateful sets. When pods in stateful set get created, each of them requests storage. And storage class is another Kubernetes concept that helps users choose between the types of storage available for the cluster. They might be different depending on the environment and infrastructure you're running on. So Azure, for example, provides Azure disks and Azure files. They might be different from the pricing perspective, like standard or premium, managed or unmanaged. You can even create your own storage classes if needed. It might look something like this, where we have a template with definition of a storage class, and we define the provisioner type, account storage type, and other parameters. So we know that users can choose storage based on storage classes. And when each pod in the Cassandra stateful set gets initialized, how does it actually request that storage? So there are persistent volumes, and they can be provisioned either statically or dynamically. Here we're talking about dynamic provisioning. And with dynamic provisioning, StatefulSet has a definition of a persistent volume claim. That is a request for storage. After the request succeeds, the persistent volume is dynamically provisioned for each pod according to the storage class that it requested. Persistent volume claim is kind of similar to a pod in context of the pod requests resources of nodes, like memory amount and stuff like this, and persistent volume claim requests persistent volume resources like size or access mode, and it creates persistent volumes that provides an API for users and administrators to actually abstract the details, the underlying details of the implementation of the storage away from users and from how it is consumed. So it's very convenient. So persistent volumes are like volumes, but their life cycle is independent from a life cycle of a pod. So now let's look at the story of persistent volume and persistent volume claim. So imagine we have a stateful set, and there is a first pod that is initialized. And this pod has a definition of a persistent volume claim with a certain storage type. And it says, I'm requesting my storage based on the storage class. Then there is a dynamic provisioner that monitors for persistent volume claims that are unbound to any persistent volume. So then it will create a new persistent volume based on the characteristics and based on the storage class that the pod requested. And after that, the persistent volume claim will end up in a bound state, and the pod will be attached to that volume. Now let's look at the actual definition of a stateful set. It's quite big here, but the main part is there is a part volume claim templates, which describes the volume claim, access mode, storage class name, resources requested. There are some Cassandra-specific parameters, number of replicas, and also some seed nodes. And let's look at an example of how to actually create a stateful set, the actual process of deploying it. So I made it a little faster. First, we can create a headless service using the kubectl create command. Then, after it's done, we are creating stateful set from that template definition. Then, after it's created, we can monitor the status of the stateful set using the get stateful sets command. And we see that there is one for Cassandra. Number of desired replicas is 5, current is 1, which is pending. That means we can describe the pod and see what is going on. And we see that there is a persistent volume claim that is actually not bound. To see what's going on with the persistent volume claim, we can use the kubectl get pvc command. And here is a new persistent volume claim in a pending status. We can, of course, get more details about the persistent volume claim that is being created if we describe it. And we see that it is using our designated storage class, managed premium, pending of type Azure disk. So if we want to see the details about the storage class that our claim requests, we see that our cluster has the following available. And we can look even further into the definition of the storage class if we use the describe storage class command. And basically, it has the entire definition of that storage class: namespace, storage account type, provisioner. So let's check back on how the pods are doing. Get pods. The container is creating, and that means that our persistent volume claim is probably already bound, and it is bound. That means that there is a persistent volume created, and there is a command get PV, which shows the persistent volumes, and it sure is bound. And basically, what we can do is monitor pods for creation until we have the exact number of replicas that we expect. So here is another one pending. They're going to be created one by one in the order, basically. And we can also watch how persistent volume claims are created. So how it transfers from pending state to bound state. Now we need basically 5 of them. And I made it a little faster, but you can see how long it takes to provision persistent volumes. If they are already created and one of the pods gets removed or something happens with it by accident, then it will be quicker because the persistent volumes are already created and they will just need to be attached. And finally, we should have all 4 of them running. Just take a second. So 4 of them are running. And we can just confirm it by getting the status of the entire stateful set. Desired number 5 and current is 5. So one of the options to experiment with Cassandra and Kubernetes without submitting any service is to create a service of a type load balancer, and that will expose an IP address that we can reach our stateful set by. It's good for interactive experiments, but it's not good to leave it open. So let's test writing data into Cassandra. So I'm going to show you an example with using my own machine to write data to Cassandra and Kubernetes. So I decided to use some public data. And because I live in Seattle, I got a data set of open addresses. And I'm going to concurrently write them to Cassandra to just test the stateful set. So I'm going to use F# functional programming language and interactive CLI because it's convenient, and why not to do that? So here I am in my code environment, importing some libraries. And here I have a definition of the type for the CSV file I'm using for addresses. It infers the type from the data. And then I'm getting the addresses and initializing a function to connect to a Cassandra cluster, to create to a key space that I'm going to be using for my table, and a function to initialize the table, and a bunch of other functions that I need for writing data in parallel manner. And then I'm using the external IP address to connect to Cassandra and get the session so that I can actually execute those functions. I'm using create house and key space with this session, creating the addresses table in Cassandra, and then calling the function to persist the addresses in parallel, and just taking the first 100 just for a test. And it should write them all in parallel. Hope it works, and it's working, and it's done. So now that we can do similar thing with Kubernetes jobs, which is another concept. It allows us to start pods and run them till completion. Also configure certain parameters like restart policy, resource limits, and other things. And we can create as many Kubernetes jobs as we want and as our Kubernetes cluster resources allow. So let's go back to that addresses example and where we write data into Cassandra and try to make it work with Kubernetes jobs. So here is a job definition file where I basically packaged my F# script into a container and made it accept 3 parameters. Because we are writing data into Cassandra in parallel, we want to basically split data in chunks and have each job for one part. So I am using the container that's called F#job, and I'm indicating the command to run that script with the correct parameters. That accepts the offset, number of records to process, and increment if we also want to use F# concurrency optionally. Now, how do we send different input parameters to each corresponding job? Well, bash is the answer. I am defining some variables to set the job count, step, and increment, and I'm using that F#job template to create many files, but with the correct parameters populated. So cool, let's see how it works in action. Let me go to my code here. F#. Okay. So I'm located in the directory of that project, and here is a F#job YAML file, the same as I showed previously. And here is the prepare jobs script that performs the creation of job files. And what we want to do is we want to execute that prepare jobs script that creates lots of files, and we can see that there is a jobs directory, and if we navigate to it, we see that those are the actual job templates that we need to use. So let's look at one of them, like 7. OK. So, and here we notice that there are 3 parameters populated with the right data that use the container image. Finally, to submit those jobs, we can use kubectl create fjobs. And this command will create all the jobs from that jobs directory. Now, we can check the status of jobs by using the get jobs command. We see that there are 10 of them. They're all successful. I mean, they're all running, and they're not successful yet because they're not completed yet. But what happens under the hood is that each job creates a pod. And we see that there are 10 pods created, and they are running. We can always look into what is happening in the pod and getting it by name. And we see that it's created from the image that was indicated in the template file. But we can also watch what the pod is doing in real time and monitor the status of our job. Oh, whoops, I didn't copy the name correctly. Let's get some random pod. Oh, it's completed. So we still can look at the logs, even after the job is completed. And here we see the output of the job. But finally, the status of jobs is visible here. And if we don't need them anymore, we can always delete all of them. And this is how it works. So now let's go back to the slides. And yeah, and by the way, the code for this example is on GitHub, F#job cube, if you would like to try it out or check. Things to note about stateful sets. Persistent volumes are not automatically removed when you remove a stateful set. It's done on purpose. In case something happens to the stateful set, you won't lose all of your data in the persistent volumes for now. And stateful sets were a beta resource before Kubernetes 1.9. Now they're out, and some people use it in production. And before considering using it in production, please go through GitHub issues that exist and make sure that there are no critical issues there. So there's also a concept of node affinity, which Eric mentioned during his talk. That means that we can tell which pods can run with other pods on the same node and other flexible settings. So there's a lot of flexibility in this way. And now let's go to a slightly different topic, but it's still very similar. We can run Spark jobs on Kubernetes since release 2.3. And I decided to try it with Cassandra on Kubernetes. So anyone heard about Spark? Everybody knows what Spark is? OK, quite a few people. So Spark is an open source project for distributed computations. It is kind of similar to Hadoop MapReduce, but it is much faster. It tries to keep data in memory. It forms a directed acyclic graph of the consecutive computation stages, and it allows optimizing data operations and like minimizing shuffling data around and other things. You can do stream processing, machine learning, data science, ETL tasks, and more. The way Spark jobs usually are submitted is using Spark submit command line command, where we can pass a jar file or Python archive. And then, yeah, so previously you could run Spark on resource managers like Yarn or Mesos. But as I mentioned, since release 2.0, it is supported on Kubernetes as a scheduler. So when you actually submit an application to the cluster with Spark Submit, there's going to be a coordinator process that is called Spark Driver. And it is managing the entire job process. And it talks to many other processes that are called Spark executors that do the work provided by a job. And in current implementation, they are implemented as Kubernetes pods. So I will show you a cool example of running Spark jobs on Kubernetes and using Cassandra to write some data and to fetch some data. So before I do that, there are a few things that I've done before I can actually submit a job using Spark on Kubernetes. So you need a Kubernetes cluster, but you also need to build a Spark image. And that is possible to do if you clone a GitHub repo of Spark, select the 2.3 or later branch. And you can build the source using Maven or SBT if you pass the Kubernetes switch. And then there are some helper scripts that help you build out the Docker image and push it to the container registry of your choice that we can indicate when we use a Spark submit command, so that Kubernetes knows what container to use when running driver and executor pods for Spark. And we also need to indicate dependency, like job dependency archives. And in the current version of Spark on Kubernetes, it is not possible to include local files with Spark submit command. So your dependencies have to be remotely accessible or pre-packaged into the container image. I've tried both. In this example, I am using pre-built dependencies. So the difference is very small. You just need to add a local colon / prefix to the dependency URL. So what is the demo? The demo is like a practical example. Sometimes you need to determine what TV show episodes to rewatch based on your preference. So who watched Game of Thrones, for example? OK, so you might have a favorite character or a favorite thing that is discussed. And I have an example where you can run a job and indicate the keyword of your preference that would scan through the scripts of Game of Thrones Season 1 or all of the seasons and build out a recommendation model with ranked episodes of which of them you might want to watch first. And I'm using Cassandra to save the search results. If somebody already searched for a keyword of preference, then we just fetch it from Cassandra. If nobody has searched for the keyword, we can do the Spark job and compute it. So let's go to the code, and I will show you what it is. So this is a Scala project. I have packaged it using SVT assembly into a jar file because I need a jar to submit using Spark Submit. There are some dependencies. Here is a keyword, which is what I mentioned. And here is the connection information for Cassandra, Cassandra cluster. And I'm using just the word Cassandra because this is going to run within Kubernetes cluster, and all the Cassandra cluster is available by this name. We have a key space that is called show recommender and a table called recommendations, loading out the Spark context, connecting to Cassandra cluster, and checking if there is already information for that keyword. If there is nothing there, we are basically looking at the scripts of the TV show and removing all the stop words and building a count vectorizer model that would tell us what episodes have the biggest occurrences of the keyword of preference we indicated. And finally, we're writing this information back to Cassandra and closing all the connections. So to make it work, there are a few things here. I need to start a Kubernetes proxy so that I can talk to Kubernetes using localhost. And here I am going to run the Spark Submit command. But first of all, I need to define a keyword. So what is your favorite Game of Thrones character from the first season? Tyrion. No more favorites. OK. OK, so we're defining a variable here. And here is a Spark Submit command. We're indicating the master URL. Deploy mode is a cluster, indicating our class that is responsible for the functionality. And I have my Spark container image that I have pre-built and included my jar into it. I'm also adding the jar for Spark Cassandra connector and including the keyword. Now, if we start this, we can start watching Kubernetes pods. Whoops, get pods. So here is a container created for the driver, and it is initializing. Now, if we look back here, it's already running, so that means there are, here in our case, there are 2 executor pods created for Spark that run the Spark job and build out the recommendation model. So they were initialized, but now they are running and performing the job. And finally, we see here that the container is terminated and the phase is succeeded. So we see that executors are terminating, and the results are actually going to be gathered on the driver, which is in a completed state. It won't be removed, so we can always check the logs here. And here are the results. So recommended episodes to watch with Tyrion are this. So this is basically the output. And we can see some other Spark job information. So eventually, there won't be any executor pods, but the driver will stay here. So now let's go back to the slides. So is running Spark on Kubernetes a good idea? It may be a good idea. For example, for a test environment or if you would like to try out a custom version of Spark really quickly, or if you already have a Kubernetes cluster and you have some spare cycles that you might want to use for running Spark jobs, or in the long term, if you don't really want to have too many orchestrators, if you already have Kubernetes and Spark runs well on Kubernetes, just use it on Kubernetes. Should I run it in production? Probably not yet, because it's very new, but it will get better, and we can help make it better. There is active development happening in this space, and you can still have a say about it if you want to change the way Spark jobs are going to be implemented on Kubernetes. And another important note is that it is quite different from running a standalone Spark on Kubernetes. So here we don't really have Spark master running all the time. These are cloud-native Spark jobs where we only have driver and executors running while the job is running. After the job is completed, all of those things are completed. The driver stays in a completed state, and executors are completely terminated. And the code for this is here, the GOTO Cassandra Spark, if you'd like to see how it works. And there are some resources that might be useful. A blog post about Cassandra. There was a talk that I gave about distributed system algorithms. I have an article about stateful sets, and all of the demos are on GitHub. So I hope you had fun. Yep. And this is me. I am Alena Hall, a senior cloud developer advocate working on Azure. Previously worked at Microsoft Research, and before that I lived in Europe and worked at many projects related to big data distributed systems, also functional programming and machine learning. And that's it. Thank you very much. You can follow me on Twitter. My DMs are open for any questions.
Thank you.